All right, welcome to our first Friday at the Fab Lab here at Amrocfablab at University Mall in Uptown Tampa. Tonight, we're coming to you to talk about 3D printing. We get a lot of questions about 3D printing, and especially right now around the holidays, people are always interested in wanting to get the best one and how do they get started in the 3D printing. So tonight we've actually got with us Chris Willingham, who happens to be my son, and has been instrumental in helping get things up and running here around the Fab Lab, and is our resident 3D printing expert and helps with our youth robotics programs and other groups that are using the 3D printers and a lot of different projects that we use them for. The 3D printers here are put to work on everything from the robotics programs to rocketry, to 3D printing parts for different machines and things like that. And we used them for doing the face shields, for protective face shields, making the frames for them, and we'll bring some of those out in a few minutes. But we wanted to, kick things off a little bit by giving folks a sort of a high-level overview of 3D printing. If you've got questions, throw them in chat, and we'll get to them as we can. If you're not able to join us live, well, this will be recorded, and you can find it on YouTube and on Facebook. So without further ado, I am going to turn it over to Chris Willingham. He's going to pop in behind me here, and he can tell you a little bit about what's going on behind us. There's actually several 3D printers. I'm blocking a couple of them. So we've got a Creality going behind us right now, printing, I believe, a brochure holder, and then a few other printers that Chris will tell you about. So here you go.
Really? Okay.
All yours.
Hi, I'm Chris Willingham. Yeah, so 3D printers.
We're working this from the same room, so this will be interesting.
Yeah.
To try to make it work.
Sorry, the setup was an interesting process. Let me stop sharing on here and share this thing. Give me one moment. Yeah. Okay, share screen. Film tab. Here we are. Okay. Oops, not sure. Hang on. Don't share that yet. There we go. There we go. Yeah. So, not sure. Yeah. From the beginning here, with 3D printing. 3D printing it's a additive manufacturing process. I just looked up this morning actually. What was that? The official definition of 3D printing is actually not necessarily additive manufacturing, but really just making a physical object from any three-dimensional digital model. Of course, if you look at that definition, that would technically mean even CNC machines theoretically count as a 3D printer, but in reality, the 3D printing we're familiar with is actual additive manufacturing, which means rather than removing material like a milling machine or a lathe, drill press, where we're subtracting material from an existing chunk of mass, we are basically extruding material or adding material to a surface to create what we want, and usually in a CNC fashion or in a digital fashion to automatically create what we want, right? With a few different types of 3D printers. We have stereolithography, which is basically high detail resin prints. These are not as commonly used. In some cases, they create extremely high resolution prints. Every layer that it creates, it uses a liquid resin actually. Yeah. It's a liquid material. It has a yeah. So it's just always comes in a bottle. It's this ABS-like resin and high temperature resin. It has a very, very wide range of different types of materials you can use. Basically, this is the material that hardens when exposed to ultraviolet light. So the SLA printers will have either a laser underneath them or a ultraviolet light filtered through a projector of some, or through a screen of some kind, to expose only the parts you want to harden to the liquid resin. So that allows you to make some really high precision parts, but they aren't necessarily there's still some downsides to that, which we'll get to later on. The most common form of 3D printing and the most accessible is fused deposition modeling. There's a few other names for it, but essentially it's this printer here. And it's essentially a CNC hot glue gun. It extrudes a layer of melted plastic onto a what we call the build plate, just a flat surface, and it's just a nozzle controlled on the X, Y, and Z axis relative to the 3D printer, right? Relative to the between the nozzle and build plate, right? There's also a lesser known technology, which is selective laser sintering. And when you hear about 3D printers that can print metal, they're usually printing using SLS. And essentially what it is, it's almost like SLA printing, except it's in reverse, and it's using a powder instead of a liquid. And that powder could be aluminum shavings or steel shavings, right? And essentially it puts a layer of powder onto a surface and then uses a laser to melt that material, harden only the material that you want, and then it moves on. It'll add another layer on top. It'll cure it again, and it will melt it again and again. It'll just keep on going until you have a finished part, right? And that's actually how you can get metal parts and stuff like that, right? That's also the most expensive by about $100,000 or so. Yeah. So most of the printers, the fused deposition modeling, like I said, the cheapest 3D printers will run anywhere from literally anywhere from $200 to about $2,000. Is it's a really wide range, and what you get doesn't have to vary that much. FDM printers are they if they're tuned well, will turn out the same. A low quality 3D printer can be tuned to turn out a good quality part, regardless of the quality of the 3D printer. But the higher end 3D printers are generally easier to get that high quality part out of, where a low end 3D printer might take, could take 20 to 60 hours of tuning and getting it just right, whereas a really high end, $2,000 3D printer, you buy it, you put it down, you put the model you want in it, and it just works, right? These particular printers are Creality CR10S Pros. If you're ever looking to buy a 3D printer, Creality is definitely a good starting point. They provide currently, I think, the cheapest FDM 3D printers available, possibly the cheapest SLA printers too right now.
Here's your question. What's the best beginner 3D printer?
Yeah, so the best beginner 3D printer, I would recommend, I've recommended the Creality Ender 3 to people before. I just recently had a little mishap with somebody picked up a Creality Ender 3 3D printer and had some quality issues. Turned out the reason behind those quality issues was it was purchased from a third-party seller, so you always want to be aware of where you're sourcing the 3D printer from. If you buy directly from Creality, they're usually pretty good quality. But the thing to keep in mind with the Creality Ender 3, I wish I had one here.
Actually, I've got a...
Yeah, it's most similar to the One Held Duplicator X3, I guess.
Yeah.
Actually, really, it's most similar to the CR10S Pro. It doesn't have some extra sensors that the 10S Pro has, but it's you can get a decent quality 3D print out of the box after maybe about a day of getting it set up, right?
We're actually running $157 right now.
Oh my gosh.
For DIY kit.
Gotta look into that. Yeah. Yeah, they get really affordable. So yeah, the Ender 3 is definitely a good starting point. There's a few others that are similar, right? The first 3D printer I ever got a hold of, I think, was an ANET A8. It's a I don't know if they sell them anywhere. It's a really low cost, 3D printer one. It's what existed as the cheapest printer before the Ender 3. So.
What are some issues when setting them up on the can you run them on every box?
Yeah. So let's see here. It's like, yeah, I mean, if you buy a 3D printer, you're gonna have to assemble it. But yeah, the main thing keep in mind. So if you're totally new to 3D printing, there's a few ways you end up with actually getting the models that you want to actually print stuff, right? Sorry, I'm trying to think of. So yeah, once you have a 3D model, well, first of all, the 3D models are actually created in a variety of different ways, right? Either you're going to design it in a computer-aided drafting tool such as Fusion 360 or Autodesk Inventor, SolidWorks, Onshape. There's a few others. These are all called parametric modeling tools. They allow you to create a detailed. Well, they allow you to create very precise, dimension models, right? Or you'll be creating it if you have something more on the artistic side. You might use the same kind of thing you might use for designing models for a game or for a film, right? That'll be 3ds Max or Blender or there's a few others. I'm actually not as familiar with the artistic side, but yeah, there's a bunch of different models. Essentially, one way or another, you're going to create either a parametric model, which is basically created from two-dimensional sketches extruded or revolved around different axes, or you're going to create a polygon model, which is going to be basically a model created by triangles, right? Once you have that model, you're going to use basically a slicer, which is a three-dimensional tool that can it's a tool that can turn the CAD file you have, computer drafting file that you have, into instructions for what the nozzle should actually be doing to create the model that you want, right? And these instructions are, literally, they're really basic. They're telling it, move from this position to that position and so on, right? Huh? Oh yeah, actually. I guess actually I can start going over. Let me first show what this, when I'm talking about parametric modeling and how you actually create the models in the first place. Now let me give me a moment. Oops. Sorry about that. Let's share this one. Okay. Oh no. It's actually freezing.
Okay. Well, you're not freezing. Your other thing is freezing. So, we're taking some time to pull up some software here. But can you talk a little bit about, we use it for the students a lot, right?
Yeah.
So when they want to learn how to do it, a lot of them are using things as simple as Tinkercad, right?
Yeah.
And can you use that as a beginning tool?
You can.
I've heard adults using it too.
There's a few things that Tinkercad teaches that are somewhat relevant to, um, professional CAD tools, such as the capability of adding and subtracting shapes to create things, which is more or less how you create things, in these engineering tools, right? But Tinkercad isn't necessarily maybe it is in the background somewhere, a parametric modeling tool, but it's not really a parametric modeling tool. And I would actually even suggest, like, for even younger students who just want to figure this out, they can probably pick up, like, you know, Fusion or or Onshape, or even even some parts of Inventor. I picked up. I started out with what was at the time called Pro Engineer. It is now called Creo Elements Pro. I'm actually not sure the state of it now. I moved beyond it because it wasn't particularly useful I found it to be a little more limiting than Tinkercad. Than Autodesk Inventor and SolidWorks, right? But it's a professional tool that is used by a whole variety of companies, including Lockheed Martin and Raytheon. I think I could be wrong on Raytheon, but pretty sure Lockheed Martin used it to design the Orion space capsule, actually. So, yeah, these tools are tools that are used professionally, and what you'll find is that they're not actually as complicated as you might imagine. They're not as, the basic idea of any parametric modeling tool is you have a two-dimensional shape. You turn it, you sketch out with precise dimensions what you want in 2 dimensions, and then you turn it into 3 dimensions, right? You extrude it up. My browser is actually crashing, so.
So, for the purposes of people interested in 3D printing, what are some practical applications of it? Are there any
practical applications? Are just without. There is actually a huge variety of practical applications. From simple things around here, when we're not using it for the more advanced use cases of robotics and prototyping products and things like that. We use it for simple things like making a brochure holder, right? Or make a toothbrush holder at my place. Face shields, right? We spent months making these at the beginning of the whole situation that's here, right? So making ear savers, which are basically we put behind face masks to actually help if you have to wear face masks for a really long amount of time. So yeah, there's a ton of practical uses, but it's not a solve everything kind of machine. Yeah, it's not high volume. Actually, the model that's running right now is another brochure holder. Estimated to take 17 hours to print. Okay, so yeah, it's not a fast machine. There are situations where you can do some degree of mass prototyping or mass manufacturing with 3D printing if you have a high quantity of 3D printers and a very small part that you want to print. The smallest part last part I looked into mass manufacturing for 3D printing was it took an hour and a half to print, and we could print 9 of them on one print bed. You can print multiple things on one print bed, by the way, but it just takes it takes longer for every single model. Took 20 hours to run one run of 9 parts. But if you have enough printers, then it still works out. But still, it's a very involved process. I can go over that.
Still jam there?
Yeah, this thing's really crashing on me. Yeah, it's very nice of this thing to just kind of completely fail right now. Okay. But yeah. Oh, I guess we might as well also go over. I mentioned there are things that 3D printers are good at, things that 3D printers are bad at. So an example of a perfect thing to 3D print is a round thing. Anything circular is going to print really well, and there's a lot of reasons. So a 3D printer has, like I said, a FDM 3D printer will have, 3 axes. It has a heated nozzle to melt the plastic. It has an extruder motor to push material into that nozzle, and it will have a heated build plate, the surface where it's actually putting your model, right? And it heats the build plate up to actually to get the material to actually stick to the build plate. By heating up the plastic, it becomes somewhat more adhesive, right? There are other approaches. You can have a 3D printer without a heated build plate, and it can print some materials. Actually, let's go over materials. With FDM 3D printers, the 2 most common are going to be PLA, or polylactic acid, or ABS, which is I actually don't. What does that stand for? Nobody remembers what ABS stands for. But PLA will melt at about 200 degrees Celsius and become somewhat adhesive at about 60 degrees Celsius. So that's usually what you'll heat. You'll heat the build plate to about 60 degrees Celsius. You'll heat the nozzle to 200 degrees Celsius, and the print will mostly work, right? If you do, with ABS, ABS melts at a much higher temperature, has different properties, and oh, you did find that. Thank you. Yes. Yes. Acrylo. That's why I don't remember it, because that is unpronounceable. Anyway. Yeah. So what I was saying is basically different models, different shape models will actually stick to the build plate better or worse. Oh, and I should also mention, if the part does not stick to the build plate or comes unstuck for a moment or in any way moves on the build plate, that part is done for. It's not going to succeed in any way. I think we probably have several examples of what we call, like plastic spaghetti, basically, that comes out of these things when the part moves from the build plate, because the build plate, the printer has, it only knows where it started. It does not know where it is for sure. So if something happens, either the part moves on the build plate or the nozzle gets jostled around, then what we get is spaghetti, which that's the inevitable result of a print failing. If you catch it early, you can stop it before it gets to this, but then you'll just be stuck with this, right? And there's several factors that can lead to this. In particular, on this one, you'll notice I'm actually not sure what the final part model was supposed to look like, but this is what the first layer looked like, right? Minus all this extra stuff, which means there was a long point going all the way out to the end here, and then going back and going around, right? This long point is a part of the model that can expand and contract as the build plate temperature fluctuates, because a 3D printer is not a perfect machine, and it attempts to keep itself at whatever temperature keep the temperature of the build plate at whatever you specify. But it's a digital machine. It'll turn on and off to try and maintain that temperature, right? Which means that it heats up and cools down very slightly by plus or minus a few degrees, which causes the material to expand and contract. And depending on the shape of your material, that can be a problem. If it's a circle, there's not really much of a problem because as it tries to expand and contract, well, circles are the mechanically ideal shape. So they will always expand and contract evenly and not much, which means it works out pretty much every time. If you have a square or sharp points like this, then that expansion and contraction will lead to a peeling effect. It'll actually begin to peel off the build plate. On a small scale, if it's a small part, that can lead to slight warping, but the part can still succeed. You'll just see the edge might be a little bit warped up. But if it goes too far, then eventually what you have is this. Right? So a way to avoid that, there are some tricks you can do within the slicing tool to actually deal with that. The slicing tool being the tool that converts your model to G code, which is a language that these 3D printers understand, or the instruction set, right? You can add what's known as a brim, which will basically it'll add more layers to the first layer outside of the shape of your model to kind of smooth out these sharp points, right? And if you have no choice but to 3D print a sharp point, that's about the best option you have. The other option is to 3D print a raft. I wish I had a raft here. Which basically it 3D prints it essentially 3D prints its own build plate on top of the normal build plate, and then it prints your part on top of that build plate. So it's a layer of plastic and then your model, and then that layer of plastic can be peeled off and thrown out, or recycled. Oh yeah. I think it just.
So frame and skirt are the same thing, or different things?
Oh yeah, I guess I didn't go for skirt. Yeah, a brim I just described as that narrows that adds more material to the first layer to kind of bevel the edges, right? A skirt actually just runs 2 or 3 lines outside of the print, but around the print. And that is usually to prime the nozzle, because again, these machines are not perfect. When the 3D printer instructs the nozzle to start extruding material, it doesn't know how much material is in the nozzle. So it'll actually take a little bit of time to begin extruding material. And there's 2 ways to actually prime the nozzle. Sometimes we use, it's always good to use one or the other. One way, the way that's usually done first is sometimes you'll see a 3D printer will create a line of material in the corner of the print of the build plate before actually making before actually starting the actual print. So that's a way it begins a prime. The brim can act as a prime, as well as a way to sort of bevel the edges on the first layer, right? And then a raft. A raft doesn't really prime it, but a raft actually extrudes a lot of extra material on the first layer, so that kind of helps out as well.
I've got a question. Oh, somebody else in here. Oh, there it is.
Tatyanna. Yes, you can, in fact, 3D print your own Barbie doll furniture if you wish to.
So where would you find it? What's the universe?
Yeah, we might as well go over Thingiverse. You may actually be able to bring it up on there and share it on there. So Thingiverse is it's where you can go to find models that you don't have to already design. I would recommend whenever pulling any models from Thingiverse, keep in mind the things that I talked about in terms of what prints work out, what prints don't work out very well, right? If they have sharp edges, sharp corners,
I'm going to search for Barbie doll furniture.
go ahead. You actually will probably find some. But yeah, if you search for corners or something like that, I mean, if you find a model on Thingiverse that has corners, or it has the other term we use a lot is overhangs.
There you go.
Yeah, so overhangs are a perfect example of overhangs. Basically, whatever direction you're going to 3D print this on, you always got to keep in mind that there's gravity on Earth. So it cannot print in midair, right? You got to imagine the way that it's printing is one layer at a time, each layer on top of the last layer, right? So if there's no material below it, then it is attempting to print in midair, and in most situations that will not work. You can print at 45-degree angles, so it can print, slightly outside the last layer and slightly outside again and again and again until you have something along the lines of an overhang, right? This is actually, even though this is SLA, this is a good example of that. You don't need supports because it's got a gradual, curve there, right? But if
Go back to the Barbie furniture for a second,
Mhm.
on the files that are there, and you grab them, I'll pull back here.
Yeah.
So if we go back over here, and there's a whole bunch of little files, right, and so you want to grab one.
I'm not sure I'm seeing it on yours.
So what are the things you look for in a Thingiverse file?
Unfortunately, I can't actually see them from.
You can see it?
Yeah.
Oh, you can see it in your view. Okay.
Causing a little. I'm having a little issue here where the browser has been crashing
Okay.
non-stop since.
All right, so but I can show it to you. So
Uh-huh.
You can see it. Turn this around. So there's a file,
Yeah.
and normally you browse through the file, right? And it's got things you can like it. You can look at the different views of it,
Mhm.
right?
Yeah.
And then there's notes.
Yeah. And those notes, if they're well detailed, first that will tell you that the person who created it had put a little thought into the 3D printing side of it. I would say prints like those, depending on the size of that, probably wouldn't print too well because they're really detailed. And 3D printers are not super precise machines, with the exception of SLA printers in certain situations, such as printing something like this.
This one gives you a lot of detail.
Yeah.
So it gives you the printing time, the full extrusion required, how to rotate it, and all sorts of stuff.
Yeah. And actually, if you look at I guess I was trying to look at the actual model. Yeah, that could print probably okay. Again, the more detail, the more precision that you demand from a 3D printer, generally the harder it's going to be to 3D print, or the less likely it's going to succeed or give you what you want, right? So usually, whenever you're 3D printing anything, I try and oversize everything as much as possible to get the least amount of detail required from the 3D printer. If you don't require a lot of detail, then you don't need a lot of detail. Sometimes it's unavoidable. This was a 3D print made to solve. Yeah, it was a prototyping project to solve a problem of a defective part, or a let's just say often defective part on a existing product. So I wanted to find some way to make a better quality part. The original part was injection molded, had a few flaws in the design, and could easily break. Yeah, there we go. So yeah, what we ended up doing is chopped it in half to try and get a side profile of it. Took out a caliper, measured everything we possibly could from it, and then remodeled it in CAD down to the inlet, input and output, nozzle parts, right? I 3D printed this originally with the intention of it only being a you know, a lot of times you can do this. You can 3D print something with the, you know, that you know probably won't come out the way you expect, right? Or won't come out at super high quality, but can give you an idea of what you're making, right? And I do that a lot actually with 3D printing, where I will 3D print something that is not intended to be 3D printed, but just intended to, you know, give me perspective, right? Because when you're CADing, when you're actually designing something, and you know, just you know, just through the digital tools alone, a lot of times you don't have any perspective on how big what you're making is or how small it is, right? And that's really one of the biggest advantages of 3D printers is, you know, you can see a physical representation of it, even if you don't intend it to be the final thing, right?
And I think that's a good point. That it's this tool that before you had these, if you wanted to fix that, what would you have done? Before you had access
before
to
this, the only option, before 3D printing, your only option would have been, well, before 3D printing, you also basically didn't have CAD, but your only option really would have been to design it, you know, either, I mean, draw it out, possibly make a physical copy using, or a physical prototype using a lathe and milling machine, maybe. You could make this in a lathe or milling machine, but it would be a lot of work. I actually looked into seeing what it would cost to get this manufactured through one of our partners, actually. The ideal solution to this actually is injection molding, and it would cost a few cents if you're injection molding it. If you're not injection molding it, it costs, you know, as a 3D printer part, at a mass manufacturing level, I think, what was the final amount? No, it's more than that for 3D printing. It added.
Moment of silence was brought to you by a crashed computer. So we are back. There you go.
Yeah, we're back. That was my computer finally dying out after, what, 20 minutes of crashing? That was pretty impressive. Hey, while you're here, I can actually show Kira. But yeah. So cost of 3D printing at a you know, from perspective of just prototyping, it's pretty much nothing. From the perspective of mass manufacturing, it can add up to, I think we actually just estimated just that we do have a way of calculating the cost of if somebody comes into Amrocfablab Fab Lab and they want something manufactured, their way of we basically take into account the cost of material, which is the smallest cost of the entire thing. The setup time can usually take, if it's not a complicated thing, 15 to 20 minutes to set up a 3D printer. And the runtime of the 3D printer, which is, you know, between the setup time and the runtime, that adds up to the highest cost. At Amrocfablab, we have a setup like $30 an hour, like $2. I normally have the 3D printer set like I think it's supposed to be at like $2 per print time hour, which is basically when the printer is on and running 3D print. You know, we charge $2 per running time of the printer, right? So even that brochure holder would cost normally $50 or so. So a lot of times, I mean,
that's seems like a high cost, and it kind of is if you're it's just the amount of time it takes to actually run these printers, right? But that's kind of that's just because of 20 hours of a machine running adds up to a lot of you know it takes a toll on these printers, right? But from a perspective of how much that would cost to manufacture without a 3D printer, actually, this was the one I did with the resin printer. Yeah, this one part manufactured on, I believe it was a CNC machine or a lathe and mill setup. It was in the hundreds of dollars for a single unit, basically, I think. It was, yeah, it adds up to a lot more, right? So, but, yeah, let's see, what we not covered. Yeah, I guess I could go over getting a model and slicing it, or showing how this kind of works out. Yeah, let's see what's in there. Let me go ahead and see.
Oh, the 3D print element more expensive than black and white.
For FDM prints, not really. For FDM prints, oh, actually, I have to click that. Hang on. Let me share that really fast. And then go back here. Let me share that. Yeah, so our color 3D prints more expensive than black and white filament ones. Yeah, not really. They're all, in terms of the PLA and ABS material, it's about the same. For resin prints, sorry. This material is the most expensive 3D printing material we have. Well, not this one. No, possibly this one. One bottle of clear resin will cost $90, and it's half a kilogram of material, versus 1 kilogram of ABS will cost about $25. PLA, 1 kilogram costs about $20, right? And you can probably buy in bulk and get it even cheaper. So yeah, on the resin side, different colors still don't cost much, but different materials definitely cost a fortune. Yeah. Oh yeah. So yeah, I was gonna get. Oops. Yeah. Yeah. So I mentioned slicers. This is a slicer. If a comment comes up, let me know. I can't actually do it here. This is a slicer, right? This is Ultimaker Cura. This is my preferred slicer. Other people prefer Prusa. Was it Prusa slicer, I think? And there's another one. There's a commercial, a paid version or paid application called Simplify 3D that a lot of people prefer. But I found the features of Cura in some ways are even equal to that of Simplify 3D. So it's a fairly good slicer. And what this tool is specifically for is taking a model. Here's another patrol order. Sure. Here's a perfect example. Okay. So a perfect example of a 3D print. This is something I forgot to mention. So 3D printed, or the models they come as well, usually one way or another end up with a STL file. That's just a file format that we use, right? That you'll either get off of Thingiverse or design yourself and then convert to STL, right? And you might throw it in here and you might find, well, this is a lot tinier than I thought it would be. And that's because STL files do not store the units of measurement that they were designed in. So see, this says 10 by 8.75 by 14 millimeters. This is likely supposed to be 10 inches by 8.75 inches by 14 inches, or 100 millimeters by 875 millimeters. Because they don't specify the units, and because this is only brochure holder, we can just plug a number in and see what it says. Yeah, this is why it's really important when you're working with a 3D print manufacturer to actually specify what the units of your file are, and to actually know what the units of your file are, right? Because STL files don't know what, they don't know if they're inches, millimeters, or centimeters, right? You can export from your CAD tool, in inches, millimeters, centimeters. If you're working with a 3D printer, you almost always want to export to millimeters when possible. And if you don't export to millimeters, then somebody's going to have to convert it by hand. And if they don't know what the units are, then they might convert it wrong, right? So yeah, in this case, looks closest to it was probably in centimeters. We're converting it to millimeters, so just scaling up by 1,000%. If it's inches, then you'll very quickly memorize that it's 2,540% that you want to scale up for to go from inches to millimeters. Other question you said? Oh yeah, yeah. So is resin plastic stronger? To us, in a way, resin plastic can be considered stronger. It is unlike FDM prints. Yeah, they don't melt. They're really resilient to heat. Yeah, I did forget to mention that. PLA, if you stick PLA in the sun, it will become pliable and it will melt. It has a higher tensile strength than ABS, at least from my research. I would recommend doing your own research to verify that, but I'm pretty sure it has a higher tensile strength. I use it in amateur rocketry and have actually had the problem of my rocket melting on the launch pad. So yeah, that's something to keep in mind. ABS is slightly more resilient, but it can still melt. And ABS will melt at like 100 degrees Celsius or something. So even in a hot car, it should be okay. But yeah, resin material, that's not going to melt. It was never heated in the first place to form it, right? It uses ultraviolet light. There's not really any heat involved, right? And this, you can also get specifically, this is high temperature resin, right? I'm pretty sure there's resins that can go up like thousands of degrees Celsius and stuff. It's a impressive. That's one of the really impressive things about resin materials, but that doesn't necessarily it doesn't necessarily mean that it is always stronger than filament plastic, because or any kind of FDM material, right? Because resin is very hard, actually. It has a higher hardness than what you might find in PLA or ABS. So that means if I put a lot of tension on this, it will break before it bends, right? There's a lot of variety of resin, so that might not be true to every resin, but the particular resin that we use tends to be have a very high hardness, and it is quite strong, but its breaking point will be a crack, right? PLA and ABS, PLA has a very high tensile strength, but it will eventually bend and then break. ABS has a slightly lower tensile strength, but still pretty strong. It will bend a lot more before it breaks. It's actually very pliable compared to a lot of the other materials that you can work with. And yeah, you can also get, there we go. Ninja Flex is a flexible filament. When this is actually printed, it becomes it's a soft rubber material actually. So not sure how the tensile strength actually compares on that, but it's that will bend a lot. Oh yeah.
resin versus for models.
Oh yeah.
The cost of it.
Yeah.
It's small.
And honestly, I did look into making my own resin material. I couldn't find a way. I looked at I mean, some of the early 3D printers used resin, but yeah, you do want to be careful. These machines cost thousands of dollars, right? So yeah. What was the other one?
Um,
Yeah. Um, yeah. So that's kind of the thing with resin is that um, you can make a high detail model. Yeah, it's really good for because that's where it excels. It still has downsides. You still have to kind of follow some of the same basic principles that you follow with you know um, FDM prints of making sure you have a decent amount of surface material to stick to the build plate, um, and making sure that every layer has another layer underneath it or a layer above it in this case, to actually print. It does print upside down, by the way, like it comes out and like that. So every layer has to be supported by the previous layer. And if it's not supported, then you have that support material. And if you got support material, very rough model. We actually, after printing this, this was one of the first experiments in resin printing by the high school kids, by Ohms, I think, and it, uh, the quality was not any better than what you get out of an FDM printer. And they eventually switched to a FDM print with that model, and it works better, I think. um, and oh, okay, yeah, and yes, if it melts, you can recycle um, back into you can reuse material, but it's yeah, there's a kit called Illustrator, I think, that lets you melt material back into um, into a, a roll basically. But it's we haven't really experimented with that. We probably should look into it. Anyway, yeah. So where was I with this? Oh yeah, so we got that. So yeah, if you have a model, throw it into Cura, hit slice, and it will kick out a very large number of how long it's going to take. Yeah. So these are all the parameters. But I just hit print without plugging in any numbers. Tells us it'll take 11 hours. We can tune things though and say there's a lot of parameters, even more than actually what's listed here. There's only a few that you really have to worry about. The shell stuff you don't really have to worry about. That's how thick the walls of the 3D prints are going to be. Those can almost always be default. The layer height will significantly change your print time and quality. If you have a lower layer height, like say instead of 0.2 millimeters for a layer, and layer height is how far up the 3D printer will move after putting down each layer. So we set that to 0.1 millimeters, for instance, and we slice. It will only move 0.1 millimeter up, and then I'll start extruding the next layer. And move 0.1 millimeter up and extrude, one after the next after the next. Yeah. For the most part, you can almost always get away with 0.2 millimeters. That's kind of the common one. Sometimes you can get away with 0.3 without a problem. Most of the time you can get away with 0.3. You can see what happens when we bring it down to 0.1 millimeters. We doubled the amount of time it takes to 3D print, right? It took 11 hours before, now it takes like 20 hours, right? We bring that back to 0.2 millimeters, we get 11 hours, 11 and a half hours, right? And oh yeah, the other thing you can adjust depending on the quality of your 3D printer. This is one area where I found that higher end 3D printers do better with. You can increase the speed that it prints at. And I have increased the speed that our current Crowd ACR10S Pros print to 150 millimeters per second and still actually come out pretty good quality for the speed that we were running it at. On an older or smaller 3D printer, what you'll find is that the 3D printer will struggle to extrude material fast enough to actually print at that speed. Either that or the stepper motors that drive all the axes will not be able to move fast enough. And you will hear it if it's not working the way that you want. You'll have to tune it back. Oh, you're talking about probably with the 0.1 millimeter. Yeah. Yeah, it can be more precise. It can give you basically a smoother finish on the sides of the 3D print, right? If you set it to 0.1 millimeters, you'll get a really smooth finish. If you set it to 0.2, you'll get a slightly rougher finish, but the difference between 0.1 and 0.2 is not really that noticeable to most people. And also you can get rid of the bridges completely just by putting on a sander, right? You can literally take sandpaper, rub it down, and you don't see anything. You can paint them too, and also there's an additional thing I forgot to mention with ABS material. You can expose it to acetone for a short amount of time to melt the outside layer and get a almost a glassy finish on the material. It's really neat. It does take a long time to figure out the exact process of doing that. And you also got to be careful. It's acetone. It's not exactly safe. So you can actually get a finish that is better than resin prints with ABS sometimes by doing that. But yeah. So so settings. Which I should also show this. It will give you a preview of what the model actually looks like, or how it's really going to create the model. It's a good idea to actually look at this. And you can actually go up and down and see, at the instruction level, like, what it's actually going to be doing, right? And follow each layer. You can see the infill, you can see the, just every detail of how it's going to work. You can also change, I'd like to set the color scheme to like speed. You can see how fast it's moving the nozzle to place each layer. You'll see the green layers here are actually, if I can get down a little bit further on here. There we go. Yeah, so green layers are infill. I didn't mention infill either. Infill is the material that goes within the volume of the model. That's not the outside shell, right? And the infill will let you. Infill is, a lot of people think when you start with 3D print, what kind of infill should we have? If you set a 3D print to 100% infill, you're going to be waiting for days for your 3D print to finish, literally. The amount of material that it takes to completely fill a model is a lot more than you'd think, and unnecessary. So when you have a solid model of some kind, you can set the infill to 10 or 20% usually, and it'll be, just as strong as if you had 100% infill, right? Yeah, if you're holding brochures, or if you're almost every use case you can think of, you don't really need the amount of strength that 100% infill gives you. And actually 100% infill in some cases won't give you additional strength at all, right? There's a lot of material science and what gives you the most strength. But for the most part, 20% cubic will get you like in almost every situation. These infill patterns, I are just different ways of filling that volume with material. If you want to get fancy, you choose gyroid and you'll get like these little zigzaggy shapes inside and all that. It really makes no difference at all, to be honest. At least for most use cases. With the rocketry, as you mentioned, you think rocketry, that's got to be really strong. You need 100% infill. Well, you got to keep in mind, it also needs to be really light, right? If I want it to fly. So I would choose the lowest possible infill possible, like 5% or, 3% sometimes, right? And it would still be fine, right? So yeah, you don't need a lot of density inside these things. Yeah, I guess that's pretty much it. Yeah, so I mean, you guys can see pretty much what that is. Yeah. So, yep. Once you got what you want, you go and save it. It'll save as G code, which is actually a programming language, basically. It gives you, oops, sorry. Wait, actually, you can't really see it. Well, anyway, you don't really have to see what that is. It's just the instruction set that 3D printer understands. You put that on a SD card, stick in 3D printer, and use the 3D printer's interface to. Oh yeah, yeah, that's true. I gotta share that too. Yeah, if you have a lot of different 3D printers, then yeah, you got to make sure you pick the right printer. Also, you got to make sure that I've made this mistake several times. Make sure you choose the right material for your 3D printer, right? If you print PLA with ABS settings, you will smell it. it will melt a lot more than it should. So yeah, you always want to be careful about that. Also, if you print ABS at too low a temperature, then it just won't be able to print it. That's pretty much it. I don't know. Are there any other questions? Yeah, less to make finished product more brittle. Actually a good question, because we kind of looked into that with this bottle cap thing, right? Because it was for a product, so we wanted to do a nice finish on it. Some research suggests that it actually makes it stronger because the layers are actually melted together better, right? Other research suggests otherwise. So, kind of unknown. I don't think I've seen any conclusive evidence one way or the other. I would think it would help a little bit because once it hardens, once it's out of the acetone and re-hardens, it is one solid material, one solid thing. All layers are gone, basically on the outside at least. Yeah, I think that's pretty much it.
I'm shorter than he is, so there we go. Let's stop sharing the screen here. Where are we sharing? Let's pull this out. All right, so I'm gonna leave Chris he's over there. There he is. All right. So we hope you enjoyed that. It was a lot of fun to do. We're going to be trying to do more of these from the Fab Lab, and hopefully we'll have. I can actually. He's almost 6 feet apart. We're also related. So anyway, we're really grateful for everybody that joined in and for the questions you all asked. We think this was a lot of fun. If you want to learn more about 3D printing or come by and learn a little bit more about it, you can look us up at amrocktampabay.com and check out some of the different things that we're doing. We had another gentleman come by earlier today who was learning more about 3D printing as well. It's a fascinating topic. We use them for a lot of different things. If there's projects you're working on or something like that, you just want to chat about it, drop us a line on the website. Thank you so much again for tuning in. And we hope you had a lot of fun. We did. And every time he goes over it, I learned something I didn't know before. So thanks again and have a great evening. And we'll catch up with you. I think our next live stream is Consumer Car Chat with Pam Oakes on the 3rd Wednesday. And we'll be back with the first Friday in January. All righty. Have a great one.